I'm Dr. David Crisp at the Jet Propulsion Laboratory in Pasadena, California, and I'm the science team leader for the Orbiting Carbon Observatory-2 mission. The Orbiting Carbon Observatory-2 is NASA's first mission designed specifically to measure carbon dioxide in the Earth's atmosphere. But not just that, it has to measure carbon dioxide with the kinds of precision needed to look for the sources that are emitting it into the atmosphere, and also something we call sinks, the natural processes that absorb carbon dioxide at the surface. This is our very first mission to do that. One might wonder why we haven't flown carbon dioxide satellites in the past to make these kinds of measurements. The main reason for that is that they're really, really hard. First of all, the carbon dioxide abundance of the atmosphere is already quite high. There's about 400 parts per million. That means about 400 out of every million air molecules is actually a carbon dioxide molecule. If we have a source of carbon dioxide, like even the largest power plants on Earth, they'll only change the carbon dioxide concentration in the atmosphere by about 1 part in 400. It's a very, very difficult measurement to make from space. We're talking about measuring a gas you cannot see with your own eyes to a precision of 1/4%. This was something we didn't know how to do up until about 2000. At about that time, by combining some of the most sophisticated technologies that we had, we could actually start to address that kind of a problem. What we had to do was to borrow detectors from systems like those used in the Hubble Space Telescope, near-infrared detectors in particular, with very high quantum efficiencies and incredibly large well depths, very low read noise, those kinds of systems. We coupled those into an optical system that had incredible precision and was incredibly fast. We were building spectrometers with a resolving power of 20,000, which is very, very high for a flight instrument, that actually could make measurements, that were fast enough that they could make measurements several times a second. In the case of OCO and OCO2, we make measurements 3 times a second. We basically take 3 frames a second as we fly around the Earth in order to keep the footprint small enough so that even in regions which are partially cloudy, we get some data. As it circles the globe 233 times every 16 days, mapping out the Earth with a resolution of about 1.5 degrees of longitude, it turns out, but then very, very high resolution from pole to pole along each of the orbit tracks. It has an orbit that's just under 100 minutes long. And during that 100 minutes, we collect about 72,000 spectra. So this thing collects spectra very, very fast. Over a day, we do about 14.5 orbits around the Earth, and that collects about 1 million spectra around the Earth. It turns out that the Earth's a pretty cloudy place, and to make a carbon dioxide measurement, to study carbon dioxide near the surface of the Earth, we need to make measurements that see all the way through the atmosphere to the surface. And clouds block most of those soundings. So we end up throwing away a lot of the data, or at least not focusing on it for full column CO2 measurements. But we still get over 100,000 high quality full column CO2 measurements every day out of this instrument. Space-based sensors, such as the Orbiting Carbon Observatory-2 and the Soil Moisture Active Passive Mission, which is being constructed behind us here, play an absolutely vital role in our capability to observe and diagnose our climate system. It gives us a vantage point that no other capability does. We see the entire Earth, and we can monitor it at a high resolution with a rapid repeat cycle, so we can monitor it over and over again as the system changes, as seasons change. And we can start to, with those systems, unravel the processes that are the physical processes that are actually operating and underlying our climate system. The Orbiting Carbon Observatory has just joined a group of 5 other satellites called the 705-kilometer afternoon constellation. This constellation of satellites includes a group of Earth science satellites that are designed to fly along a very, very similar series of orbit tracks and cover the very same parts of the Earth's atmosphere and surface right after each other, actually within about a 40-minute period every day. Instead of referring to this as the 705-kilometer constellation every time, most of us just call it the A train. So OCO2 leads the A train. JPL addresses several different aspects of the climate change problem. First of all, we do build systems like the Orbiting Carbon Observatory-2, which monitors carbon dioxide, both emissions and absorption by the system. The emissions by the system are the climate forcing. So once we force the climate and it starts to change, how do we monitor its response? Well, the atmospheric infrared radiometer system, the AIRS instrument on the Aqua satellite, just 2 satellites back from us, measures atmospheric water vapor and atmospheric temperature very, very precisely, and we can watch those change as time goes on. Between the Aqua satellite and the OCO2 satellite is the GCOM W1 satellite, the Japanese satellite that measures surface temperature and the near-surface water abundance very, very precisely. Absolutely critical parts of the climate system as well. Another instrument on the Aqua satellite, the MODIS instrument, actually makes maps of every kind of growing thing on the Earth, whether they be trees or crops or over the oceans, plankton and how it's growing. It gives us critical information about the health of the oceans as well as the land biosphere. Now, behind the Aqua satellite, we have 2 satellites designed to measure clouds and aerosols. We first have the Calypso satellite, which is a LiDAR satellite that makes very, very precise measurements of aerosols through the Earth's atmosphere. These are the fine particles that make up smoke or dust or smog. Then right behind it, just a few seconds, 30 some odd seconds behind that, is the CloudSat satellite. This is a satellite that uses a 94 gigahertz radar to measure not just the tops of clouds, but all the way through the cloud profile as it flies along. This has really revolutionized our understanding for how clouds are forming in our atmosphere. One of the biggest uncertainties in how the climate might change in the future is how clouds might respond to the changing climate. Will the Earth become cloudier? That'll reflect more solar radiation and it might cool it back off. Or will it become less cloudier? Maybe it absorbs more carbon dioxide or more sunlight and heats up more. We don't know. So systems like CloudSat and Calypso are critical for answering questions like that. And then finally, there's the Aura satellite making measurements of ozone. JPL has 2 very, very important instruments on the Aura satellite. The microwave limb sounder measures ozone and all of the gases, or many of the gases, that are responsible for its destruction. It uses a microwave-based system. Then we have a high-resolution Fourier transform spectrometer called the tropospheric emission spectrometer, which makes measurements through the stratosphere down to the surface so we can actually map out ground-level ozone as well as stratospheric ozone and see how those processes are changing over time. Another critical part of our climate system that has to be monitored. So that picks up the tail of the A train. That's the caboose. Currently, natural processes at the surface of the Earth, trees on land, and the oceans, are absorbing over half of the carbon dioxide that human beings have been adding to the atmosphere every year. The interesting thing is, we don't know what those processes are. We don't know where those processes are, and we don't know for how much longer they're going to continue to operate in this fashion, absorbing half of all of the carbon dioxide we emit. So this is one of the main questions that the Orbiting Carbon Observatory-2 is going to be answering as it orbits the Earth and takes very precise measurements of carbon dioxide. This is, in fact, an absolutely essential question to answer as we go forward, because carbon dioxide is the primary driver of man-made climate change. It's the primary tuning knob we have on our climate system. So we have to understand both the man-made processes and the natural processes that are controlling its buildup in the atmosphere.